Hey guys, sorry I ran out of time in that last video, but I was just summarizing at the end. So I'm going to try to get through this video kind of quickly as well. You'll notice that I have the exact same problem here, same masses of hydrogen and nitrogen that I'm starting with. How many grams of ammonia can I make? How many grams of the excess reactant are left over? Same balanced equation. Well, this time what I'm going to be doing is I'm going to be using a table that is referred to as a before, change, and after table. So this is before the reaction begins. So in other words, what do I have with the starting amount? By how much do those amounts change during the reaction? And then how much do I actually have at the end of the reaction? Okay. And your book actually sort of references this as well. So notice that I actually made a BCA table here before you guys showed up. And B is before, C is change, A is after. You'll notice that I've got my balanced equation written right above in this nice little chart here. What you need to know, though, guys, is that the only thing that you can enter into a before, change, after BCA table is anything that's in the unit of moles. All right. So in this equation, though, in this problem, I told you how many grams I had before the reaction began. So what I'm going to have to do is I am going to have to do a little math before I can dump those things into the table. So to the right of our BCA table is where we're going to be doing any sort of before math that has to happen. So what does it say here? It says we have 27.0 grams of hydrogen and 120.0 grams of nitrogen. So what I'm going to do here is I'm going to quickly go ahead, show my work as always, and I'm going to convert my grams of hydrogen into moles of hydrogen, which is 13.4 moles of hydrogen. And then I'm going to go ahead and take my grams of nitrogen and convert that into moles of nitrogen. And when I do this, I get 4.283 moles. And the reason why I sig figged it here, guys, is because I know I'm going to be doing some subtraction with it later. So that means I have 13.4 moles of hydrogen that I'm starting with and 4.283 moles of nitrogen that I'm starting with. And you know what? Before the reaction starts, I haven't made anything, so I don't have any of that product. So you maybe notice here that I left a lot of room in between the balanced equation and the question versus the BCA table. That's because I need to do some explaining of some things that we're going to go ahead and put into the BCA table. So what we need to do here is we need to what's called normalize. We need to normalize the amounts of each of the reactants that we have. And by normalize, I mean we're going to take the amount of moles that we had in the before row, and we are going to divide it by the coefficient that is associated with that. Okay, so if I want to go ahead and do that for nitrogen, I have 4.283 moles, and I divide it by 1 because it's an understood coefficient of 1 right there. So divide it by 1. So this equals 4.283. For the hydrogen, it's 13.4 moles, and I'm going to divide it by 3. Again, I'm dividing it by the coefficient there. And when I do that, I get 4.46. Now, I'm only doing this with the reactants. Well, what does this all mean? Well, the lowest normalized amount comes from the limiting reactant. You guys learned about what that limiting reactant was in that previous video. So this is my lowest amount. So I'm going to be thinking about that. And then, therefore, I know then that nitrogen is going to be the limiting reactant. Therefore, I'm going to have some leftover hydrogen. Now, the other thing about this normalized value, this lowest value, is that it's going to represent the value x. Now, I'm going to explain what this x means, and this is going to maybe seem a little complicated, guys, but bear with me from beginning to end, and I think it's going to kind of make sense in the end here. Okay, so when I have a chemical reaction, I always know that my reactants are going to go down because they're going to get used up. So I'm going to know it's going to go, my change is going to be a negative, whereas my amount of my products is going to go up. So that's going to be a positive value. And I'm going to think about how do these values change in reference to that x value that we talked about versus how do these values change in terms of the actual number of moles that we started with. So what I'm going to do is I'm going to use that coefficient again. And what I'm going to do is I'm going to multiply it by that value of x. So this is the coefficient for the nitrogen. And in terms of the hydrogen, that's going to change by 3x. Why 3? Because that's the coefficient. And then my ammonia is going to go up by 2x. Coefficient of ammonia is 2. All right, well, what does that mean in terms of moles? Well, guys, we know what x equals. So that means my nitrogen is going to go down by 4.283 moles. My hydrogen is going to go down by 3 times 4.283 moles, which is equivalent to, it's going to go down by 12 let's see how many sig figs, 85 moles. And this is going to go up by 2, multiplied it by x again, which is 4.283. So therefore, my nitrogen is going to go up by 8.56 moles. Okay, so this is the value of 2. You guys are going to get all over my case right now because I messed up some sig figs, but I'm going to move on so you guys can figure out my sig fig mistakes later. Now, if I know that I started at 4.283 moles, and if it goes down by 4.283 moles, that means I don't have any nitrogen left. Whoa, that's what the definition of limiting reactant is. Now, in terms of my excess reactant, if I started with 13.4 moles and it says the change is negative 12.85 moles, then that means I'm going to end up with 0.6 moles. Here, hey, look at me. I looked at my sig figs. That goes to the 10th place. That goes to the 100th place. So I needed to round to that 10th place. And then in terms of the moles of ammonia, then this is going to go up by 8.56 moles. All right. So remember my questions were, how many grams of NH3 can I make? How many grams of the excess reactant are left over? So that first question there, if I am making 8.56 moles of ammonia, this is what I'm making. If I go ahead and I convert that into grams, 17.04 grams of ammonia per mole, what that means then is I will be making 146 grams of ammonia, which is what we figured out in that last video. And then if I have 0.6 moles of my hydrogen that's left over, that's what I have after. If I multiply that by 2.02 grams of hydrogen per mole of hydrogen, that means with sig figs, I'm going to have 1 gram of hydrogen left over. Now, I know I messed my sig figs up there, guys, but whenever we look at our answers, the sig figs in their answer will always depend on the method that you use. Okay, so in this case, it truly will be 1 gram with only 1 sig fig, and in the previous video, it had 2 sig figs. All right, So think through this one. Look at your notes. Look at your notes on the other way of calculating.